Hi Math 30-2s, welcome to our first video lesson. So, as the review from last week suggested, we are going to be working on Chapter 6, Exponential Functions. So, I provided you with a student copy of these exact same notes that I'm going to work with, and I will also post a completed version for those of you who prefer just that instead, okay? So we are looking today at lesson 6.1, exploring the characteristics of exponential functions. Okay, I'm going to switch over to a full screen view because I don't think you really need to see me so much. So that'll just take a second and it'll look weird for just a minute. There we go. Hopefully that is working. So, as I said, we're going to do 6.1, exploring characteristics of exponential functions. So to start us off, what exactly is an exponential function? In our last unit, we studied polynomial functions where we had the variable as the base and we had numbers that were exponents. An exponential function is the opposite. It is a function in the form of f of x where the variable is the exponent. So a times b to the power of x. Now we do have a couple restrictions here. So it does say that a cannot equal 0. Well, that makes sense because if you're multiplying by 0, then the entire thing would just equal 0 and you would have nothing. Now, there's two restrictions or two things that need to be true for b. The first is that b has to be greater than 0. What that means is that b has to be positive. We're not going to have a negative base. And the reason for that, if you recall from previous math classes, when your base is negative, the result of the equation will change between positive and negative values depending on what the exponent is, right? So negative 2 squared is positive 4, whereas negative 2 cubed is negative 8. So we don't want that flip-flopping between negative and positives. So we only use positive values for b, the base of the power, and we see there that b also cannot equal 1. And the reason for that is because 1 to any exponent just is equal to 1. So nothing actually changes if our base was a 1. Okay? So now what does that function actually look like when we graph it? It looks like this. This is what is known as exponential growth, where we start off really small and the change is really tiny at first. We're just getting a little bigger and a little bigger. And then at some point, the growth or the increase in the function just starts getting huge really, really fast. And just as a side note, exponential growth is what is happening with the COVID-19 virus. That we started off really small and then more and more people are getting it and it's following an exponential growth curve. And that's what viruses and bacteria and lots of things in biology actually work on exponential growth. Anyway, just a little side note there for you. Okay, so let's take a look and compare the graphs of two different exponential functions. So we've got 2 to the power of x and 1/2 in brackets to the power of x. And the reason the 1/2 is in brackets, which is important, is that the entire 1/2 then is our base. All right, so let's break these down just a little bit. So for the first one, y is equal to 2x. What is the value of a? Well, there doesn't even look like there is an a value right there, right? We see the base 2, we see the exponent x, but there's no number multiplying that. And when you do not see another number, so something multiplying the power, that's because a is equal to 1. And multiplying by 1 is redundant. Writing that you're multiplying by 1 is redundant, so we don't have to write that we're multiplying by 1. We have 1, 2 to the power of x power. Our b, which is our base for our function, is 2. And in the second one, 1/2 to the power of x, same thing. There is no other number in front of the 1/2 that we are multiplying by, so that means our a value is 1, and the base of this function, or the base, of the power is 1/2. All right, so let's take a look at what happens when we go to graph these. Now I'm going to Which mode's on you just slightly? Sorry for this. All right, so because we're actually going to do this together, so I need to depart from the PowerPoint. All right, so let's do this together. So we're first going to graph y is equal to 2x using a table of values. So I've picked some values for the exponent to be -3 through +4. All right, so let's get to work here. If the exponent is -3, what that means is we have 2 to the power of -3. Now remember from grade 10, we learned that negative exponents told us to take the reciprocal of the base, so that would be 1 over 2, and now the exponent becomes +3. So we can evaluate that. 2 to the third is 2 times 2 times 2, which is 8. So 2 to the -3 is equal to 1/8. 2 to the -2 would be similar, right? The -2 exponent tells us to take the reciprocal of the base, which would be 1/2, and then the exponent would become +2. And 2 to the power of 2 is 2 times 2, which is 4. So this would be 1/4. 2 to the -1 would be take the reciprocal of 2, which is 1/2, and then the exponent would simply be a 1, which means we would have 1/2. Now what happens when the exponent is 0? Remember that any base to a 0 exponent is equal to 1. That was our 0 exponent law from grade 9. And now it gets easier. So 2 to the power of 1, well, that's simply 2. 2 to the power of 2 is 2 times 2, which is 4. 2 to the power of 3 is 2 times 2 times 2, which is 8. And 2 to the power of 4, we're going to take that 8 times it by another 2, and we would get 16. So now we're going to graph these on that coordinate grid you see there. So I'm going to start when x is 0, y is 1. So that's our y-intercept right there. There we go. When x is 1, y is 2, which is our base. So that's there. And now we see how the growth is increasing. So when x is 2, y is 4. When x is 3, y is 8. And I don't have 16 on here. Now on the negative side, we're getting smaller and smaller. So when x is -1, we're at a half. When x is -2, we're at a quarter. So I'm only making estimates of where these are now. And when x is -3, we're at an eighth. So we get this very typical exponential curve. Now as you can see there, we are going to get closer and closer and closer to 0, right? The greater, or the smaller in this case, that x becomes, the closer and closer we are going to get to 0, but we're never actually going to hit 0. This is what is known as an asymptote. That is a line that the graph approaches but never actually touches or intersects. Now, no matter how small our x value gets, we could have x to the -100, right? 2 to the 100, that would be 2 to the power of 100 when x was 100, not x to the 100. 2 to the 100 is 1024. If we were doing 2 to the -100, that's 1 over 1024. Super small decimal, but not going to be 0. So that's what's called an asymptote. And the equation for the asymptote when it is the x-axis is that y is equal to 0. Because every point on the on the x-axis to here has a y value of 0. All right, now let's take a look at the reciprocal function. When x is still the exponent when the base is 1/2. When we have 1/2 to the -3, that would tell us to take the reciprocal. Well, what's the reciprocal of 1/2? It's 2. So now we would have 2 to the +3. Well, that equals 8. And we saw 8 here in the previous function. So we're going to get these exact same numbers, just in the opposite order. 2 to the -2, 1/2 to the -2 would be take the reciprocal, and that's a little messy, sorry, let's clean that up. Let's try that again. So 1/2 to the -2 would equal the reciprocal of a half, which is 2, to the power of +2 now, which is 4. 1/2 to the -1, again, we take the reciprocal, which would be 2, and it would simply be +1 exponent now, which would give us a y of 1. Sorry, a y of 2. Getting ahead of myself. Now when x is 0, 2 to the power of 0, or sorry, again, 1/2 to the power of 0 is equal to 1, the 0 exponent law. Now when x is 1, we're just going to have our base of 1/2. When x is 2, 1/2 squared, well, that's a half times a half, which is a quarter. 1/2 to the power of 3 is a half times a half, which is 1/8. And lastly, 1/2 to the power of 4 would give us 1/16. So what we are going to get is the mirror image of our first function here. So we have the same y-intercept. When x is 0, y is 1. Only we have the positive values, the large values of y, are happening when x is negative. When x was -3, we had 8. When x was -2, we had 4. When x was -1, we had 2. And then as we get into the positive x's, this is where we're getting the tinier and tinier fractions of a quarter, or a half, a quarter, an eighth, and a 16th. And we're getting the exact same shape of the function, only the mirror image of it. So like that. Okay? Make sense? All right. So moving along then, I've just given you the reminder note about domain and range. We already know though, domain is all the x values, range is all the y values, and the intercept is either an intersection where two graphs cross each other, or if we're talking about a particular axis intercept, like the x-intercept or the y-intercept, we're talking about where the graph crosses the x-axis. So let's look at some of those things now for these two graphs. And here I've given you the pictures of the two graphs. So what is the domain of both of these functions? Well, as we can see, there is no limit to the x's we could have, right? X can be any real number on both of them, right? There's no reason to have a restriction, or there's no restriction on the x values. So for both of these, our domain is that x can be any real number, or the way we write that again is with that e for element. So x is an element of the reals. Now what's the range of our function? Well, there is a restriction now on the range, right? We're only seeing positive values for the y values, right? We're not going into the negatives, we're staying only here in the positive. And we talked about the fact that we are never going to actually hit 0. We'll get really, really close to it, but there is no way to equal 0, right? Because our denominator can't be 0, and as long as you have a 1 in the numerator spot, you are never going to equal 0. So our range then is that y needs to be greater than 0, because it has to be a positive number, as we saw in our graphs. Can't equal 0. So for both functions, the range is that y is greater than 0 and y is an element of the real numbers. Now what about the x-intercept? We saw that they both had the exact same x-intercept. They have x-intercepts here at 0, 1. And that is because, again, of that 0 exponent law. Any base to the power of 0 is equal to 1. Okay, now what about our y-intercept? Sorry, I got those confused. Sorry, guys. Our y-intercepts are the same, that x is 1. Try that again. Our y-intercepts are that y is 1 when x is 0. Sorry about that, guys. All right, so let's go back and take a look at what our x-intercepts are. X-intercepts are where we cross the x-axis. And in fact, do we cross the x-axis? Answer to that is no, we don't. So there is no x-intercepts. So there are none. Okay, but we definitely have a y-intercept, and that is based on the zero exponent law, so y is equal to 1. And lastly, the equation of the asymptote. Well, what line are we getting very close to but never crossing? We are getting close to the x-axis. What is the equation of the x-axis? That is that y is equal to 0. Again, the reason for that is because every y value on the x-axis is equal to 0. Now, sometimes students get a little confused by that. If it's the x-axis, y is the equation, y is equal to 0. Well, think about it. On the x-axis, the x is changing all the time. X is 1, x is 2, x is 3, x is 4, right? So the equation can't be an x because the x is changing. Y is the same, y is always 0. So that is our summary for domain, range, x and y intercepts, as well as the equation of the asymptote. Okay, well, let's continue on then. So the last thing is about basically end behavior, to link it back to what we talked about polynomials. So when y was equal to 2x, we got what kind of graph? This we would refer to as an increasing graph. So as long as, or not as long as, when y was equal, or f of x was equal to 2x, we got an example of an increasing function. Now when y was equal to 1/2 x, we get a decreasing function, right? So when our base was a fraction, we got a decreasing function. Okay, now this I've included in your notes, but I've already said this to you, that what we noticed when we graphed 2x and 1/2 x was that we get mirror images of each other. They are reflections in the y-axis. All right, this next part of the note, I want to flip back to my PowerPoints because I want to see something. I want us to see something. All right, so I'm going to go back to this. All right, so we're going to go from here now. So what I want us to look at is we're going to explore what happens to an exponential function when we multiply it by different values of a. So we're going to use the same base. This time, though, I'm going to change that base to 3. So we're going to use the function y is equal to 3x. So what does that look like when we graph it? Looks like this. So the only difference really here is we still see our y-intercept of 1, because 3 to the power of 0 is equal to 1. But now when x is 1, y is equal to 3, as opposed to last time, y was equal to 2. So we're a slightly steeper graph here. All right, now what happens when we multiply 3 to the power of x by another number? So let's take a look at, well, what happens when we multiply it by 2? Well, when you graph it, you get this, right? And if we think about that, all it means is we're going to take every value in the original function, y is equal to 3x, and times it by 2. So 2 times 1 means that our y-intercept moves up to 2. Instead of when x is 1, y is 3, it would become y is 6, way up there, right? So we've just kind of stretched the graph or pulled the graph up by a factor of 2. Same thing will happen when we multiply it, say, by 5. We're going to really stretch it up this time, and the graph of that looks like this. So we're just pulling the graph up by a factor of 5, and we see that really clearly here in the y-intercepts. When x is 0, the original function is equal to 1. Now, 3 to the power of 0 here in the function is still going to be equal to 1, but now we're going to times it by 5. And so we see that here in the y-intercept of the green function. It's at 5. Now what happens if we multiply it by a half instead of multiplying it by a whole number? Well, we're actually going to kind of push the function down, because instead of our y-intercept being here at 1, it's going to be down at a half, because 1 times a half is a half. So we've kind of pushed the function down. So that's what happens when we multiply an exponential function by some coefficient. Now the other thing I want to show you is what happens if that value a is a negative number. So here, y is equal to negative 3 to the power of x. Notice that the negative 3 is not in brackets. So our base is not negative 3. Our base, our b value is still 3. We are multiplying by negative 1. Again, writing the 1 is redundant, so we will often just see it as negative 3 to the power of x. But this means that our a value is actually negative 1. Our b is still the 3, and our exponent is the x. What that looks like now is a reflection in the x-axis, or across the x-axis. Instead of our y-intercept being at positive 1, it's now down here at negative 1. And now the same things are going to happen if I multiply by other numbers other than negative 1, but negative, let's say, 2. I'm again going to stretch this function, only now I'm going to stretch it down. So instead of being here, our y-intercept at negative 1, it's now going to be at negative 2. Exactly. And if I multiply it by negative 5, we're going to pull down even more and have our y-intercept be down here at negative 5. And if I multiply by only a half, a negative a half, our y-intercept is going to be at negative a half. So here we can see what happens when we multiply an exponential function by a coefficient. We actually end up stretching or pulling up the function when the number is bigger than 1. And here when we saw we had fractions, we actually found that the function got basically pushed down a bit. All right, so let's complete this form then. I'm going to switch back out of this again. Sorry, I know that makes the screen a little annoying. Hi there, sorry. All right, so let's continue on then. Let's do a summary of that chart. So, what is the value of a in y is equal to negative 3x? It was negative 1. What was the y-intercept? Again, if you want to go back up, what was the value of the y-intercept when x was negative, when a was equal to negative 1? It was negative 1. Oh, isn't that interesting? Look, they're the exact same. What was the value of a when we have y is equal to negative 2 times 3 to the x? Well, it's negative 2. And again, what's the y-intercept? Oh, again, it's negative 2. It's the same. I think we've got a pattern. So what's our value of a when y is equal to negative 5 times 3 to the x? Of course, it's negative 5. What's our y-intercept? You got it, it's negative 5. And when y was equal to negative 1/2 times 3 to the x, our a value is negative 1/2, and so was our x value, our y-intercept value was negative 1/2. So there we've got the note that we take every x-coordinate, we take the x-coordinate of every point in the graph of y is equal to negative 3 times x, and we multiply it by the numerical coefficient when we are stretching the graph by a factor of that numerical coefficient. So again, just kind of stretching it by a factor that is equal to a. And when we have the negative a's, we see that it's a reflection in the x-axis. All right, so here's a summary of what we've learned so far. So the domain, x is an element of the reals. Now what's the two differences between the two columns? In the first column, we're saying that a is positive. Right? A is a positive value. And in the second column, we're saying that a is negative. However, that does not change anything for domain. X is any real number. It does, however, change something from range. Here, y is going to be greater than 0 when a is greater than 0. And when we flip it across the x-axis, when a is negative, we found that our range would also flip. Y is negative. So y is less than 0 now, right? We saw that in those graphs. What's our x-intercept? There is none. And that's true for both functions. We're going to get very close to hitting the x-axis, but we don't actually get there. What's our y-intercept? We just saw in the previous chart that y-intercept was always the value of a. And that's true for both. Regardless of whether it's a positive a or a negative a, the y-intercept is the same as that value of a. And what's the asymptote? Again, the asymptote is related to the range. So when the range is greater than 0, the asymptote is y is equal to 0. When the range is less than 0, same asymptote, y is equal to 0. In both cases, we're getting really close to 0, but we're never touching it. All right. Hopefully this all makes sense, guys, right? And again, the reflection then, we saw this in the graphs. When our a is negative versus when it's positive, we are getting a reflection in the x-axis this time. All right, now what I'd like us to do, so I'm going to switch over now to my graphing calculator, and we're going to take a look at when we change the base of the function this time. Sorry, I'm just flipping through my notes to get the same page up as you do, so when I go over to my graphing calculator, I've got it. So here, let's get our graphing calculators out. Okay, so I'm first asking you, let's just use the base function of 2 to the power of x. So go into your graphing calculator, into the y equals, and we're going to do 2 to the power of x. And let's graph that. So yeah, there we're seeing our typical exponential growth curve. Now let's take a look at what happens. Well, we kind of already know what happens, right? What happens when we use a half as a base? Now you can type this in one of two ways. You can either type it in as a fraction. Remember to put your fraction in brackets. So 1 divided by 2 as your base. Close that bracket, and now exponent of x. Or of course, the other way you could do this, what's 1/2 as a decimal? That's 0.5 to the power of x. Both will get you the same thing. Now we already know what that one looks like because we graphed that earlier. All right, so we're getting the mirror image in the y-axis. All right, we also should know what's going to happen when we do -2 to the power of x. Well, we saw that that was going to get us a reflection in the x-axis, and there it is. All right, so the blue and the black one are mirror images of each other in the x-axis. The blue and the red one are mirror images of each other in the y-axis. And what happens when we graph -1/2? So -0.5 to the power of x. Well, we should already be able to guess that one as well. Yeah, there we go. We're getting another reflection. All right. Now, what happens? Let's take a look. What if I use something other than 2? So let's go with 4. I'm going to keep all my 2's up here. Well, actually, let's do this. I'm not going to keep them all up here. Let's clear this one out, and this one out, and this one out. But we are going to keep our original. So what happens if instead of 2x, I do 3 to the power of x? What would that look like? So I still have the same y-intercept, and that we were not seeing when we changed our values of a. When I changed the values of b, we still have the same y-intercept of 1, but after that, the graph gets steeper. And what if we did something like 5 to the power of x? What would that look like? Again, even steeper, but still having the same y-intercept. Still going through 1 on the y-axis. And again, what happens if we change the base? Well, again, we already saw this. If we change the base to be a decimal, so let's see, what if we did 0.2 to the power of x? We're getting a steeper line, but it is, or a steeper curve, but it's decreasing this time instead of increasing. Okay, so let's do a summary then of what that all means. So here I've actually just included this one, but let's walk through it together. What does this mean? So when b is greater than 1, so the base of the exponent is greater than 1, and a is greater than 0, meaning it's a positive number, you are going to get a graph that increases from left to right and is above the x-axis. When we flip that and we make the a value be negative, we're going to get a decreasing graph and it is below the x-axis. Right? This is when we were going to get one that looks like this when it's on the coordinate grid. Right? Whereas this one, we were going to get one that looks like this, is above the x-axis. Okay? Now, when b is in between 0 and 1, meaning it's a proper fraction, and a again is greater than 1, that's when we get that decreasing graph. We get that mirror image graph, right? So 2 versus a half is the base. We get a decreasing graph, but it's still above the x-axis. If we also make the a negative, that's when we're flipping down to be below the x-axis. And this time, when the base of the function is negative, that's when we're going to get an increasing function. And again, I can go back to my calculator. And if I just rewrite everything quickly, we'll just see that again. Right, so what we're talking about is this. When b is positive and a is positive, we're getting an increasing graph that is above the x-axis. When b is positive but a is negative, so something like -1 times 2 to the power of x, that's when we get a decreasing graph and it is below the x-axis. So we're starting off high and we're getting smaller as x gets bigger. So that's a decreasing graph. If we flip the base to be a fraction or decimal between 0 and 1, so let's say we do 0.4 to the power of x, we are going to get a decreasing function that is above the x-axis. So we're starting high and we're getting low as we move from left to right. Conversely, if we multiply that decreasing function by a negative number, so -1 times 0.4 to the power of x, we are going to be below the x-axis, but it is an increasing function. It is getting bigger. That's what that all means there. Okay? All right, so let's just do a summary then. What are the characteristics of exponential functions? So the y-intercept is always 1. Oh, sorry, I need to rewrite that. It's not always 1. We found that it depended on the a value, right? So our y-intercept is actually always the value of a. Because remember, if we were multiplying by something, we multiplied by 2, we multiplied by 3, we multiplied by 5, and I multiplied by half, and we saw we stretched up. So our y-intercept is the value of a. There is no x-intercepts. So either 0, we'll say no x-intercepts. The x-axis is the asymptote, or the horizontal asymptote specifically. Okay, the domain is always x is an element of the reals. Now the range depends on the value of a. When a is positive, the range is that y is greater than, greater than 0, not greater than a. But when a is negative, then y was less than 0. We saw that as well. Now, it also says that the values of a and b determine whether the graph is increasing or decreasing. So when a is greater than 0, so meaning it's positive, and b is greater than 1, we got an increasing graph going from left to right. And specifically, we are above the x-axis, so we are going from quadrant 2 to quadrant 1. When a is positive but b is a decimal or a fraction from 0 to 1, we got a decreasing graph. This is just summarizing all the stuff we've already seen. So we get a decreasing graph going from, again, quadrant 2 to quadrant 1, meaning we're above the x-axis. However, when we flip things around and we make a be negative, that's when we saw a decreasing graph if the b value is greater than 1. So we're in quadrants 3 and 4, so this is when we're below the x-axis, and we're going down as we get bigger x values. When b is a fraction or a decimal between 0 and 1 and a is negative, we actually get an increasing graph when we go from quadrant 3 to quadrant 4. Okay, this is just summarizing all the stuff that we just looked at with our graphing calculators and in the previous chart. So we're just putting it all together. All right, now when we change the values of b, the curve gets steeper as b increases. So the bigger the value of the base, the steeper the exponential curve is. And the curve gets steeper when b is a decimal as b decreases. So the smaller the value of b when it is a decimal. So a graph with a base of 0.1 to the power of x is going to be much steeper than 0.8 to the power of x. Okay, again, we've seen all this. We're just putting it into summary charts. So this is the assignment I want you to give a try. Just 3 questions. Workbook page 143. I gave you the workbooks on your Google Classroom last week. There are a couple example questions above these practice questions for you to take a look at. And we'll have a Google Meet next week. So if you have any problems or any questions, anything you're not sure of, you can ask me those then, okay? And always you can email me, okay, guys? All right, good luck. Give this a try.